The lesson topic for this video is geometric probability. So geometric probability is the ratio of two measurements. And these measurements can be length, area, volume, and even time, because time is a measurement as well. Now, if you take a look at the image to the right here, you see a couple of circles. Let's imagine that this is a dartboard. And let's say I gave you a dart and I said, throw the dart, and if you hit the red circle, you get a prize, and if you don't hit the red circle, you don't get a prize. And we're going to assume in these types of geometric probability situations that you do hit somewhere within the large circle. So you don't hit out here, or down here, or over here. You do actually hit the circle. What's the probability that it would land in the bullseye portion of that circle? So that's an example of geometric probability. And we're going to learn how to find that probability during this lesson. So if it's a ratio of the two measurements, it might be the length of what you want. Again, that's kind of in quotes what you want. Let's say what you want is to hit the bullseye, okay? So the length of what you want out of the total length, or the area of what you want out of the total area, or the volume of what you want over the total volume, or the time that you want out of the total time, whatever the situation is. Let's take a look at some examples. Okay, so this example says find the probability that a point placed at random on the segment MN will fall in the indicated segment. So we see some geometry notation that we haven't seen for a while, and that is, for example, segment MN. So the question is, what's the probability that if I randomly put a point somewhere on this segment, that it would be on segment MN? So think of it kind of like Battleship. Somebody puts a ship somewhere and you're trying to guess where it is. So somebody put a point somewhere, you're trying to guess where it is. What's the probability that it's on segment MN? Well, this entire segment right here, anywhere on this length, would be success. And so we know that probability is success, which from 10 to 14 is 4 units. Success divided by the total number of items in your sample space, or in this case, the total length of segment MP. So from 10 to 20 is 10 units. So 4 out of 10, or 0.4, or 40% likelihood that it would land on segment MN. All right, so the same thing for segment NO. Well, from N to O is from 14 to 19. From 14 to 19 is 5 units. So the probability would be 5 is the length of success divided by the total number of outcomes, which is the total length of the segment, which is again 10. So 5/10, or 1 out of 2, which is 0.5, which makes sense because if you can look at this, this is 50% of the line. All right, so really quickly, NP would be 6 out of 10, and OP would be 1 out of 10. Okay, so here's a little bit more advanced example. It says find the geometric probability of an object being in the shaded region. Again, if you picture a rectangular dartboard, and you will for sure hit somewhere on the dartboard, I want to know the probability that wherever that lands, okay, I want to know the probability it will land in the shaded region, the blue region in this situation. So what we would need to know is we would need to know the total sample space. Now the sample space would be the entire area of the rectangle, so we have to find that. And then success would be measured if you hit the shaded area, so we need to know the area of the shaded area, shaded space, and then we'd have to write the ratio for our probability. So the total area is found by multiplying the base of the rectangle times the height. Okay. Well, the base of the rectangle, remember from geometry, we have 3 units plus 2 more units plus 3 more units. So that's 8 units for our base times the height, which is shown as 5 units right here. So 8 times 5 is 40, so the area of the entire rectangle is 40. So there are 40 square feet, because it's measured in feet. There are 40 square feet on this quote-unquote dartboard, okay? Now find the area of the shaded space. Well, the shaded space is a triangle. All right, so the triangle formula is 1/2 times base times height. So the area is 1/2 times the base of the triangle. The base of the triangle is 2 times the height of the triangle. And the height of the triangle is from here to here, perpendicular to the base, which is again 5 feet. So 1/2 times 2 times 5, well, 1/2 of 10 is 5. So the area of the triangle is 5 square feet. So now we can think of our probability of what's the probability I'm going to land in that shaded space. Well, there's 5 square feet of area that would be success, and there's 40 square feet total area. So our answer is 5 out of 40. In other words, 1/8. So there's 1 out of 8 chances that we will land in the shaded region. Okay, I'm going to give you a couple of pieces of information for this one, and then I'm going to ask that you pause the video, try this one on your own, and then check to see how you did. So the question is, what is the probability, again, just like the previous example, what's the probability of landing in the shaded space? Okay, if I threw a dart and did indeed hit this circular dartboard, what is the probability that it would be in that triangle? Remember, we're not using the fact that you might be a very good dart thrower in these examples. All right, a couple things you might want to remember. That is that a radius is from the center of the circle out to the edge, so that's a radius right there. It's also a radius from here to here, and all these things might come in handy. Also remember the area formula for a circle is pi r squared. All right, try the example and then check to see how you did. Okay, so the area of the circle is pi r squared, which is pi times 14 squared. Again, the radius, for example, here is 14 because the same radius was here, 14. 14 is the radius, so we have 615.752 for our area of our circle. And then the area of the triangle, the shaded area, I used that height that I'm showing in red there, and this is the base. Well, notice they're both 14. So the base of the triangle is 14. The height, the perpendicular height from the base is also 14. So 1/2 times 14 times 14. So that's 98. So then lastly, the probability of landing in the shaded region is 98 over 615.752. This ends up being about 0.159, so about 15.9% chance. Okay, this last example, we're going to have to draw our own picture for this situation. It says you have a rectangular board that is 24 inches by 35 inches. So 24 by 35. In the center of the board is a hole with a radius of 5 inches. Now it doesn't say what shape the hole is, but since it says there's a radius, it must be a circle. So in the center of the board there's a circle hole with 5 inches right here for the radius. It's kind of hard for me to draw that in there. I could have drawn it bigger. So that's 5 inches. Find the probability that you throw a beanbag through that hole. So if you imagine like a beanbag toss game, what's the chances that you throw that beanbag in this hole out of the entire wooden board? Again, you might be a very good beanbag player, but that does not matter. We're just finding a general probability. So same thing, we need to find the total area again. Find the total area of the board. That's going to be base times height. And that area is 35 times 24. $840 is our total space on that wooden board. Find the area of success. Well, success would be to have that beanbag drop through that hole. So we need to find the area of the circle, which circles are pi r squared. So pi times the radius of that circle, we said the radius is 5 squared, and we'll compute that. Get 78.540 if rounded accurately to 3 decimal places. So what's the probability of landing in the hole of that beanbag board? 78.540 out of 840. Again, that doesn't seem to tell us much, so it's probably best to convert this to a decimal to see what that's really saying. It is 0.093, so about 9.3% chance that you will get the beanbag through the hole.